This is going to be the first of several videos in which I break down a type of reaction known as redox reactions. So redox stands for reduction oxidation. So oftentimes you'll hear them refer to oxidation reduction reactions as well. So what's happening here is that sometimes in certain types of reactions you'll occasionally get one atom that effectively drops in charge by gaining electrons, while simultaneously another atom in the reaction mixture effectively increases in charge by losing electrons, right? And in fact, specifically, the electron that is losing, or I'm sorry, the atom that's losing the electrons is giving those electrons to the atom that's gaining these electrons. So the way you can remember, one phrase you want to remember is called Leo-Ger. Leo stands for lose electrons oxidation. Ger stands for gain electrons reduction. So the atom that is losing electrons is getting oxidized, and the atom that's gaining electrons is reducing. Now you might say, well, if it's gaining electrons, how is it reducing? Because doesn't reducing mean it's going down? Well, remember, electrons are negatively charged, right? So if you're gaining a negatively charged particle, your charge is going to go down, right? Now, so it's not the number of electrons that is being reduced; it's the effective charge on that atom, right? And you'll see this more in the next video when I actually show different types of redox reactions. So first, for the rest of this video, what you need to know is you need to be able to assign oxidation numbers. Now, oxidation numbers, they aren't technically the charge on the atom, but that's how I want you to think of them. They're effectively the charge on each individual atom within a molecule. So there are 8 different rules for assigning oxidation numbers, and you need to know this because when you are trying to determine if a reaction is a redox reaction, you need to assign an oxidation number to every single atom in the reaction on both reactants and product sides to then compare oxidation numbers and see if there's been an appropriate change. And again, that will make more sense to you in the next video when we actually go through multiple examples of redox reactions. So first, let's talk about the rules for assigning oxidation numbers. Rules for oxidation numbers. And so capital ON, that's just shorthand I'm using for oxidation numbers. So the first rule, any element in its elemental state has an oxidation number of 0. Sorry, that's supposed to be 0. So what does that mean? Well, like for metals, let's say copper, for instance, the elemental state, the natural elemental state of a metal is as a solid monatomic element. So just a single atom, a single solid atom of that element. The one exception is mercury, which is a liquid. So if you see copper like that, that's going to have an oxidation number of 0. Oxygen, for instance, the natural elemental state of oxygen is as a diatomic gas. So it's O2, 2 oxygens bonded together in their gaseous state. If you see that for oxygen, that is its natural elemental state. So for that, each oxygen atom there would have an oxidation number of 0. Right? The second rule says any monatomic ion, so that's an ion of just a single atom. For any monatomic ion, the oxidation number equals the charge. Now, for each of these, I'm only going to give 1 or 2 examples just for the sake of brevity. But when we are working together through Zoom and on some practice problems that I'll provide you. I will definitely give you more examples for all of these as well. So right now, let's say we have, for instance, magnesium 2+. That's a monatomic ion because it's an ion formed from just a single atom. So the oxidation number is just the exact same as the charge. The charge of that ion is 2+. The oxidation number is +2. Rule number 3. The sum of all oxidation numbers in a molecule or ion, or polyatomic ion, must equal the total charge. So for instance, let's say we have CH4. This is methane. There is no charge on it. You know that because if there was a charge, we would have to see it right here in the upper right-hand corner. Right? So if there's no charge on that molecule, that means the sum of all of the oxidation numbers have to equal 0. So that means that the oxidation number for carbon plus 4 times the oxidation number for hydrogen, because, and I just say 4 times that because there are 4 hydrogens here, right? That must equal 0. Let's say we have sulfate, or a polyatomic ion. So the charge of this entire polyatomic together is -2. So that means that the sum of all of the oxidation numbers has to equal -2. So we say the oxidation number of sulfur plus 4, because there's 4 oxygens, so 4 times the oxidation number of oxygen must equal -2. That's what that rule means. Alright, rule number 4 states that all group 1 metals will be +1 when in a molecule. So basically, it's just saying if it's not in a molecule, then that just means that it's by itself. So that would fall back to rule 1 if it's just in its elemental state. But if group 1 metal is involved in a compound or a molecule, it will always have a +1 oxidation number. So NaCl, for instance. Sodium is a group 1 metal. It's in a molecule. Its oxidation number is definitely going to be +1, no exceptions. Rule 5 is very similar. It says group 2 metals will always be +2 when in a molecule. So, for instance, let's say we have magnesium chloride. Mg, oops, went to black a little bit early there, but that's alright. So MgCl2, magnesium is a group 2 metal, and that's in a molecule, so its oxidation number will be +2, right? Always. Rule 6. When in a molecule, fluorine is always -1. So basically what that means is unless fluorine is in its natural elemental state, which is diatomic fluorine, and that would of course fall under rule 1, fluorine will always have an oxidation number of -1. So let's say we have HF. Well, that is not the elemental state of fluorine, so fluorine has to be -1. Alright, rule 7. Hydrogen has an oxidation number of +1 when bonded to nonmetals, and -1 when bonded to metals. So let's say, for instance, we have NaH and HF as two examples. So in this first one, NaH, so that's sodium hydride. Sodium is obviously a metal, so hydrogen is bonded to a metal. Its oxidation number there would be -1. And now remember, if we're going back to the rule about group 1 metals, that they have to be +1, there is no charge on this molecule, so the sum of the oxidation numbers have to equal 0. I just said hydrogen is -1, sodium has to be +1, +1 and a -1 equals 0, so that makes sense. Here, hydrogen is bonded to fluorine, which is a non-metal, so bonded to a non-metal, it's +1. And also, in the rule previously, I said fluorine has to be -1, so +1 and a -1, once again, equals 0, makes sense. And the last rule, which I'll finish this video on. So, when in a molecule, oxygen has an oxidation number of -2 unless it's bonded to fluorine, directly to fluorine, or in a peroxide. Right? So if oxygen is bonded directly to fluorine, so let's say, for instance, we have OF2. Fluorine's rule supersedes oxygen, so fluorine would have to be -1 here, and there's 2 of them, so there's no charge on this molecule, meaning that it has to add up to 0. So the 2 fluorines, each with an oxidation number of -1, that gives us -2, which means to cancel that out and give us a total sum of 0, the oxygen here would have to be +2. And now a peroxide is something like H2O2, for instance. So it just has the general formula X2O2. Hydrogen peroxide is an example of that, and that's H2O2, but it's not the only example. So if you see this formula, that's a peroxide. And in a peroxide, oxygen has an oxidation number of -1. But unless you have one of those 2 exceptions, in every other molecule that oxygen is involved in, it's going to have an oxidation number of -2. So those are your rules for assigning oxidation numbers, and in the next video we will I'll show you how to apply some of those.